So yes, thanks for CSIR for inviting me to give this presentation. And here we go. So here is the disclaimer, similar to CSIR's, I guess, that the lawyers like, and no, I'm not going to read through it. So here is our presentation outline today. A brief introduction about critical and strategic minerals, their definition and importance. Talk a little bit about lithium, its properties and uses, past, current, and forecast demand. Where is it produced in the world today? Where does it occur within the WCSB? And a recent history of Petro-Lithium exploration and development and some current operator activity. Do something similar for helium, its properties and uses, past, current, and future demand. Where is it produced in the world? And where does it occur within the Western Canada Basin? Then we'll look at recent helium development in the basin and some current operator activity in Saskatchewan, which is actually quite a hotbed of activity these days. Then I'll end up with summary and conclusions. So this is Canada's critical and strategic minerals list. So on March 11, 2021, Canada unveiled this critical minerals list, and the list comprises 31 minerals, all found in Canada. These minerals are essential to Canada's economic security, required for its transition to a low carbon economy, and they're a sustainable source of economic source of critical minerals for international partners, such as the US, the European Union, United Kingdom, Australia, Japan, and South Korea. So this list actually includes minerals used in various strategic industries, such as clean energy, consumer electronics, critical infrastructure, agriculture, advanced manufacturing supply chains, and defense. And the consumer applications of these substances include batteries, solar panels, magnets, and wind turbines. And there's lithium, and there's helium. So moving on, here's lithium. There's its chemical symbol. It's a third element on the periodic table, and it's an alkali metal, I should say. It's low density and lightweight. It's the lightest of all metals. Has a high specific heat and high thermal conductivity and a high electrochemical potential. When we see it in nature, it's as either lithium salts or as a component of minerals such as spodumene, which is a lithium pyroxene. And these particular chemical properties make lithium useful in many industrial and high-tech applications. So if you look at evolving use of lithium by sector, here's a pie chart from 2010, over 10 years ago, compared with one from 2020, and you can see some differences. Specifically, the amount of lithium that is used for batteries in 2010 was 23% of the whole of the pie, whereas just last year that had actually more than tripled to 71%. So I mean, although lithium is used in the creation of rubber and plastics, pharmaceuticals, it's added to aluminum to decrease its strength in aerospace applications. It's used to provide cooling, remove CO2 and control humidity. It's used in lubricating greases and heat resistant ceramic and glass. If you think of your stove top, it's used in that. Your glass stovetop. Most importantly, though, it is used in the manufacture of batteries, and it's lithium-ion rechargeable batteries, which are really driving this growth in consumption. And as I said, the proportion of lithium used in battery applications is more than tripled just in 10 years. So it's this ever-increasing demand for rechargeable lithium-ion batteries for consumer electronics, power storage, and transportation that really continues to drive, if you'll pardon the pun, current and future demand. And this is because of the need to increasingly limit CO2 emissions. Lithium-ion batteries are used in transportation for passenger and commercial electric vehicles. And these are responsible for the increase in forecast demand. So where is it actually coming from? Where is this lithium coming from? It's coming from four main sources: spodumene, hard rock mines; salars, salt lakes in places like South America. There are lithium-rich clay minerals, in the Southwest US, as well as oilfield brines in places like Canada. This is the so-called Petro-Lithium that you may have heard of. So most lithium production and most of the reserves are held by Australia, Argentina, Chile, as well as Bolivia, the latter three countries forming the so-called lithium triangle of South America. There's really no significant lithium production from North America at the present time. So therefore, you have these long supply chains needed to supply minerals, to supply these, to produce these rechargeable batteries. Just as a point of interest, current lithium carbonate prices are about $31,875 a ton right now, based on Chinese import costs, because China imports a lot of lithium. Just 1 year ago, there were only 7,727 Canadian dollars a ton. So there's a huge demand for this, and it's driving up prices. So looking at each of these sources in turn, we can look at lithium from hard rock mining of pegmatites. Lithium occurs in conventional ores, primarily as spodumene, that lithium pyroxene and pegmatite deposits. These are medium to large size deposits confined to unweathered ore body extent. These typically contain the highest lithium concentration of these four sources. Heavy machinery is used to excavate them, typical drill and blast activities. So to access these, it's quite energy intensive and expensive. As well, there's use of chemical reagents for refining. So here's a shot of the Greenbushes hard rock spodumene mine from Western Australia. Lithium from salars or saline lakes. So this is the extraction method used in the lithium triangle area of South America. These are large deposits where the lithium is in solution as a brine at shallow depths, a few tens of meters below the surface. So this brine is pumped to the surface into evaporation ponds. You can see in the pretty picture here, where it's concentrated by evaporation in this hot, arid climate. So this is actually quite an inexpensive process, but it's also quite slow, taking 1.5 to 2 years to get a concentration of lithium that can be used. As well, because they're pumping water into these lakes, there's local concerns from Indigenous people regarding fresh water use. So here's the SQM lithium mine in the Atacama Desert, Chile. Geothermal lithium is another source of lithium brine. Here, lithium and other strategic minerals are dissolved in hot subsurface brines, which are currently being produced to generate geothermal energy, I should say. The extraction and sale of lithium from these brines can actually benefit the economics of geothermal power production. There are projects currently under development in Southern California, USA, and here's a picture of the Salton Sea, also in Cornwall in the UK and in the Rhine Valley of Germany. So there is actually a potential to produce significant amounts of lithium. Southern California alone could produce over 600,000 tons of lithium carbonate per year. However, this particular source is still in the early stages of commercialization, and direct lithium extraction or DLE processes have yet to be worked out. So lithium can also come from clays. Here's the Clayton Valley project in Nevada in the Southwest US. And these are somewhat hybrid deposits comprised of hectorite clays as ore, and hectorite being a lithium-rich montmorillonite, smectite swelling clay. So these are accessed or excavated via heavy machinery on surface mines. Ponds are then used to leach and concentrate the lithium chloride that's produced. These are small to medium-sized deposits and still in the early stages of commercialization. All right, near and dear to our hearts, here's Petro-Lithium from oilfield brines. Now, these are deep, unconventional brine resources, unlike the South American shallow salar brines. And here, the lithium is extracted via wells from high-rate, high-water cut, end-of-life oil and gas reservoirs. In fact, when they're extracting lithium, this produced brine becomes a new revenue stream rather than a waste product. These are lower cost and less energy intensive than hard rock mining, and direct lithium extraction allows faster processing than lithium sourced from salars, those saline lakes in South America. These actually provide a really awesome opportunity to leverage both existing oil and gas infrastructure, as well as an experienced workforce that exists in Western Canada. Pause for water. So to look at a history of lithium exploration in the Western Canada Sedimentary Basin, there was a wellhead brine sampling program conducted by the Alberta Geological Survey, the Saskatchewan Geological Survey, and the Geological Survey of Manitoba from the 1990s through the present day. So these programs provide information about lithium concentrations as well as other elements broken up by location and formation or depth. You don't always have that formation. This extensive data set is available in the public domain, although Alberta has the most data as their sampling commenced earlier. Also, as required by law, Petro-Lithium operators who are public companies submit National Instrument 43-101 technical reports containing data from their own wellbore sampling programs. These are also publicly available. So the data set for Alberta is much more extensive than that for Saskatchewan or Manitoba in terms of numbers of samples taken and number of stratigraphic intervals sampled. All right, here's the good stuff. So this is the Petro-Lithium distribution in the Western Canada Sedimentary Basin. The way we set this up, the cool colors are the lowest concentrations, where you see the dark blue, and the highest concentrations are found where you see the red dots. So we find that we highlight the areas with the highest concentrations. These are actually occurring within the Devonian. So based upon sampling from the various provincial geological surveys, the highest concentrations of lithium are found in these Devonian age strata, particularly found in association with major reef structures. So these are the Beaver Hill Lake, the Swan Hills and Slave Paint formations, the Woodbend Group, the Leduc Formation in Alberta, and the time equivalent Dupereau Formation in Saskatchewan, as well as the Wabamun Group strata. So I'd like to talk about a little bit about at least one schematic model for lithium mobilization, Petro-Lithium mobilization into some of these aquifers in the Devonian that are in west central Alberta, specifically the Fox Creek area. So lithium mobilization and enrichment is associated with the following. These are alteration of silicates, where we have lithium and potassium-bearing minerals within the Precambrian basement. You have direct contact between Devonian waters and that Precambrian basement, or mobilization of silicate-bearing fluids into the aquifer, aided by deep faulting, as you can see in the cartoon here. We find that these enriched lithium values are positively correlated with dolomitization, and there is a speculative genetic association with underlying Precambrian terranes. So major element ratios of these brines indicate potassium enrichment, suggesting water rock interactions involving silicate alteration. As well, the data indicate that these brines were highly influenced by dolomitization, as I said. This is because of their low magnesium and high calcium brine ratios relative to seawater. And strontium, lead, and lithium isotopic data indicate that these brines are isotopically similar to Precambrian basement and or hydrothermal vent fluids, indicating that these brines experience significant silicate alteration and are possibly associated with hydrothermal fluids. So the Precambrian basement may actually be the ultimate source of the lithium. So areas of higher lithium concentration may correspond to areas exhibiting significant deep faulting, like the Peace River Arch. You can see that a little bit here. In areas like this, deep-seated faults which bound the arch provide a vertical migration pathway from these postulated Precambrian lithium sources into overlying carbonate reservoirs. As well, permeable plastic wedges shut off the arch could also provide secondary pathways for fluid mobilization. So here's lithium concentration overlain on an aeromagnetic map of the Precambrian terranes. So if we look at the lithium concentrations, and they are quite high in this area that I'm highlighting with my cursor, which I hope you can see. So these also show up a possible, though speculative, correspondence with the fault-bounded edges of these Precambrian terranes, such as the Snowbird tectonic zone and the Kimawan isotopic anomaly, basically where it's the confluence of these two zones. So the lithium, according to this one model anyways, for this one particular area, may be related to fluid flow coming up along these shear zones at these terrain boundaries and charging these Devonian reservoirs. So if we look at metallic and industrial mineral rights by operator, so this is showing you a lot of the major players in the lithium space across the Western Canada Basin. So we have players like E3 Metals here in the red that have been around for a few years now, as well as newer people on the scene, such as Petro-Lithium, which are down here in Saskatchewan, that have only been around more recently looking for lithium. And one interesting thing here is that Deep Earth Energy has also got lithium rights, and they are down here right along the US border here. So I think they have plans for lithium, even though they are a geothermal company. Not all companies are identified, but the majority of the operators here listed will be Petro-Lithium operators. And if we overlay lithium concentrations on the areas that they've staked, it's really no surprise that the areas with the highest lithium concentrations are the areas where these operators have acquired these rights. And just a little bit, a quick talk about rights here. Mineral rights for lithium or any metallic and industrial mineral are acquired slightly differently in each province. In Alberta, these resources, along with those of superficial deposits such as sand, gravel, and any mineable substance, except for oil sands and coal, are included under metallic and industrial mineral rights and must be obtained separately from PNG rights, even if they're hosted within an oil or a gas producing geological zone. Similarly, in BC, they are referred to mineral and placer rights. In both Alberta and BC, these rights are obtained via applications made directly to the Crown for specific areas. There's no bidding process, such as occurs with PNG rights. The only restriction beyond the payment of application fees is that the rights in question not already be under disposition. Once obtained, these metallic rights are maintained through rental fees and work requirements. In Saskatchewan, rights to brine minerals are included under subsurface mineral rights and are also separate from PNG rights, but have been granted via a competitive bid process since December 2018. These rights for the brine minerals are posted 3 times a year in April, August, and December. All right, I said I would talk about DLE, direct lithium extraction, and there are really 3 main groups, 3 main categories to go about it. These are adsorption, ion exchange, and solvent extraction. The first of these, the adsorption, physically adsorbs lithium chloride molecules onto the surface of a sorbent from a lithium-loaded solution with water as a potential stripping solution. Think of this as the lithium chloride is being soaked up by a sponge, and then you're wringing the sponge out subsequently. That's a reasonable analogy. Ion exchange, the second process, takes lithium ions from the solution by trading lithium ions for protons or other cations within the sorbent structure. An acid solution is typically required for stripping and recovering the lithium. So this is sort of like an ion exchange you might have in your water softener at home. The third process, solvent extraction, exchanges lithium chloride molecules or lithium ions between brine and an organic liquid phase containing an extractant that complexes with the lithium or lithium compounds in the brine. So to be successfully deployed, whichever of these DLE techniques is being used, it must be able to extract lithium from complex brines with high concentrations of other ions such as sodium, potassium, calcium, magnesium, borates, and sulfates. So lithium summary. Lithium's unique properties make it an essential component of industrial and high-tech industries. Increasing demand for lithium is forecast as a result of global decarbonization policies and the move to lithium-ion batteries for transportation. It's currently, production is currently dominated by foreign sources with long supply chains. There's a need for a reliable domestic source of lithium. Our own Western Canada Basin hosts abundant lithium resources as Petro-Lithium within oilfield brines, mostly within these Paleozoic age reservoirs. Multiple operators have acquired the rights to develop this resource. And direct lithium extraction from many of these operators is currently undergoing laboratory and field testing, and it's the last major hurdle before full-scale commercialization. So lithium is also known as white gold. So I submit to you that the white gold rush is currently on. All right, it's the end of part one. Hope you got a charge out of the first part, where the second part is a little lighter, or hopefully you'll be enlightened. Sorry about the bad joke. So helium overview. It's the second element on the periodic table, and it's the second lightest element after hydrogen. It's a noble gas discovered in 1868 during a solar eclipse, and it's named after the Greek word for the sun, helios. It's inert, it's a monatomic gas, and it has the lowest boiling point of any element. So these properties in particular make helium an integral part of many industrial and high-tech applications. Similar to like we did for lithium, we can look at the evolving use of helium by sector. In 2016, you can see that this was the breakdown for helium. MRIs are using a lot. It's used as a lifting gas for welding, leak detection, as a breathing gas for medical applications, as well as diving applications. And semiconductor and fiber optics manufacture is a relatively small slice of the pie. We look at it 5 years later and keep your eye on that semiconductor and fiber optics manufacture. That's actually more than doubled. It's nearly tripled, not quite tripled in those 5 years. So helium's largest growth to date in the past 5 years and in the future is where it's used for manufacturing fiber optics and semiconductors, as well as LCD screens. So it's in the high-tech industries where the greatest demand growth has occurred. If we look at global helium production and reserves, we see that the United States has significant reserves, and they have historically provided most of the global production. Other big players in the game in terms of production currently are Qatar, as well as Algeria, and Canada is in there, but we were just a blip on the map, at least back in 2019, before things really started going. So again, most of these global helium suppliers are outside of North America. Places like Russia, like I said, Qatar, Algeria, Poland, even South Africa is getting into the game, as well as Australia. But yeah, very long supply chains. And my next slide does kind of speak to that. If we look at global helium production and demand by region, So the US has fallen off in its production. As we compare 2019 to the forecast for 2022 next year. So US production has fallen away, and places like Russia, as they bring their major gas projects online, they're going to produce LNG, and they can produce helium as a side product of that liquefied natural gas process. So Russia is about to become quite a major player, and other places like Qatar and Algeria in the Middle East. Whereas the regions where the helium is consumed, North America, and specifically the US, still is the largest consumer of helium. So the sources of helium are decoupling from the major users of helium. And these are moving into, shall we say, politically challenged areas. So why is the US no longer producing as much helium? Well, this is because of the shutdown of the US National Helium Reserve. So the Helium Act in 1925 authorized the US Bureau of Land Management to build and operate 6 helium plants and establish a helium reserve at Cliffside. And you can see it, it's the little dot down here, the northwest part of Texas. So what this reserve is, these are mid-continent gas fields in the United States that have appreciable concentrations of helium, up to a few or several %. These are all connected by pipeline, and they have fed into this storage facility at Cliffside. In 1960, the US Congress changed the US government's role from producer to conservator of helium, and contracted with natural gas producers to sell crude helium to the federal government for storage at Cliffside. In 1996, they approved the Helium Privatization Act, ordering the US government to sell off most of the 29 BCF of reserves due to the high cost of maintaining this facility. So at one point, the US was actually providing up to 35% of the global helium supply. And as this Bureau of Land Management storage facility sell-off of helium occurred over the last 2 decades, it's kept the price artificially low. So moving on, in 2013, Congress approved the Helium Stewardship Act to auction off all of this remaining, the remaining helium assets, including the remainder of the federal spot stockpile, to private industry. So federal helium storage remaining in the US is only about 2.5 BCF as of this month, and all of this is exclusively reserved for US government usage. And as of the end of last month, from what I've read, BLM is no longer managing this federal helium reserve, and none is accessible to private buyers, only for the US government. So that being said, if we look at past, current, and future supply dynamics, the blue here is the US supply, and you can see that as that storage of helium was sold off, the supply that the US is providing to the world is decreasing. And you have this shift of significant helium production to areas outside of North America. Here's Qatar in the red, Russia in the brown. Canada and other are here at the very top, and Australia and Algeria are in the darker zone here. So this shift of production to areas outside North America includes jurisdictions with significant geopolitical risk, such as Russia and the Middle East. As well, you can see that there's a potential shortfall between production and demand, depending on demand growth rate. If the growth rate going forward is 3%, we may just make it as things stand. But if the demand growth rate is higher, say 6%, then we're going to see a serious shortfall. So we're going to have to step up our game. That is, private industry will have to step up our game. So this is really where Canada can step in and help to fill this gap beyond what you saw in that previous forecast. As outlined by Kornbluth in his geoconvection talk last month, Western Canada has significant advantages. Number one being minimal geopolitical risk compared to other areas of the world. A really close proximity to the United States, which is still the world's largest helium market. As well, similar to when I spoke about lithium earlier, we have access to an immense public subsurface database from past and current oil and gas exploration, as well as a reasonable royalty and regulatory framework. I'll just digress here briefly, talk about helium separation and purification. When helium is pulled out of the ground, it's even 0.35 mole percent helium is considered a high concentration, but this still has to be separated out from the other bulk gas components. There are three principal technologies which are often combined depending on the composition of that gas stream. Membrane separation. It can be upgraded or purified using high pressure membranes, which either concentrate or purify helium through selective diffusion of the smaller gas molecules through microscopic pores in a physical medium. Secondly, there's pressure swing absorption or temperature swing absorption. These technologies use temperature or pressure to cause selective adsorption of different size gas molecules into the medium. The large surface area consisting of uniformly sized pore spaces. Cryogenic separation is similar to air separation units that are employed in the industrial LNG business. This technology uses low temperatures to cause different gases to condense off as a liquid in the fractionation tower. So you can pull off the methane and the higher the other hydrocarbons. You can pull off nitrogen if you drop the temperature low enough, and what you've got left is helium as a leftover project, because its melting point or boiling point is so low that it remains a gas phase. As well, there are different types of helium grades that we talk about. Increasing purity as you go towards the top of the list. Grade 4, which is 99.99% purity and lower, down to about 80%, is pejoratively described as balloon grade. As you go up in purity, these have different applications. Grade 4.7 is 99.997 purity. That's known as grade A helium. Cryogenic applications, pressurizing and purging. The next grade up has military applications. So these are sort of the industrial grade helium. As you go to the very top, the highest purity helium, which is 99.9999% purity, is used in semiconductor chip manufacture and in LCD manufacture as well. This is the research grade helium. The reason you're getting, the way you get the names of these, grade 4 is occurring because there are 4 nines in the purity. 4.5 is 4 nines and a 5, so it's 4.5, and so on and so forth. Grade 6 simply has six nines in the purity, both before and after the decimal. Once the helium is purified, it is typically liquefied, if it's just as LNG is prior to shipping around the world. So it'll fill a smaller volume. Liquid helium product also addresses a wider market, including the end users who require the low temperatures of liquid helium. In larger helium plants, the gas is liquefied and stored into these 40-foot long ISO intermodal shipping containers, as you can see here. Due to the high value of helium, it can also be economically shipped regionally as a gas in high pressure tube trailers, although the shipping costs for the helium gas are higher than that for liquid helium, because you're storing less mass of helium in the gas phase. And I'll point out that at the current time, there are no helium liquefaction facilities that currently exist in Canada. If we want it liquefied, we simply compress it and send it south to the States. All right, helium, origin and abundances. Helium is fairly rare on Earth, as we'll see, but it actually comprises almost a quarter of the universe's mass, and it's actually the second most abundant after hydrogen. Most of this helium was produced in the minutes following the Big Bang, about 13.7 billion years ago. So you are here right now. There's the Big Bang, and you had helium as well as lithium actually produced within the first few minutes after the Big Bang. Helium is also currently produced within the sun and other stars through the process of nuclear fusion, which converts that hydrogen to helium. Two reactions, which I'm not going to go into because I'm not an astrophysicist. One is the proton-proton chain reaction. This occurs in lower mass stars like our sun, or the carbon-nitrogen-oxygen cycle, which occurs in higher mass and therefore higher temperature stars. On Earth, let's get down to Earth here and get on with it. Terrestrial helium is actually produced through a natural radioactive decay of elements such as uranium and thorium and in minerals, typically felsic minerals. The results of this reaction are an alpha particle containing 2 neutrons and 2 protons, which is a helium nucleus. This is positively charged and will actually it'll pick up 2 electrons from its surroundings and then form a helium atom. As I said, although helium is common in the universe, it's quite rare on Earth, 5 parts per million in the atmosphere, and its bulk crustal concentration is 8 parts per billion, although it can occur within deep natural gas deposits at concentrations up to 7%. So where is it in the subsurface? So as I mentioned, it's produced by uranium and thorium bearing minerals, which decay typically within felsic and granitic basement. Older crust has a greater potential to produce and accumulate helium because it has more time to radiogenically produce that element. Primary migration out of the host rock occurs via fluid flow. Advection is a fancy word for that, aided by the presence of faults and fracturing. And this fluid flow involves the heating above mineral closure temperatures, typically above 70 degrees Celsius, in the presence of a carrier gas, such as nitrogen or carbon dioxide, to remove helium from the minerals. This follows with a secondary migration of the helium, which is typically a lateral movement with these associated gases like nitrogen and or CO2 once the primary migration has occurred. This can occur via free gas migration, groundwater movement containing the helium and nitrogen, or the stripping of gases from groundwater by migrating CO2 or hydrocarbons like methane. It's trapped typically within structural traps. These can be drapes over domes or anticlines, or even horse, as you can see in the diagram here, or thrust faults. And the reason that this occurs in it's trapped structurally is that stratigraphic traps are more difficult to seal. And this is due to the atomic size of helium, which is 0.2 nanometers, which is significantly less than that for methane, which is 0.38 nanometers. Therefore, there are more stringent criteria for its trapping, and it typically requires a cap rock with very small pore throats. So evaporites, things like salt or anhydrite or kerogen-rich shales can provide an adequate cap rock, or even regular shales, provided you have maybe hundreds of meters of them. It's useful to compare petroleum systems with helium systems in terms of source maturation, migration, accumulation, and trapping. And you can see here for yourself, petroleum comes from organic matter, and helium comes from radioactive decay. Maturation is through burial and heating. helium, its time to accumulate within the crust, as well as the volume of that crust. If there's more felsic material that can produce that helium, that's better. Primary migration for petroleum is pressure driven, whereas in helium, it's heated to above mineral closure temperatures, fracturing of the rocks and minerals, and any mineral dissolution that may occur to produce that helium and get it out of those minerals. Secondary migration is buoyancy driven for petroleum, and it is also buoyancy driven to some extent for helium, but groundwater and stripping can also play a role. It accumulates in reservoir beneath a cap rock, and here it is exsolution in the presence of an existing gas phase beneath that cap rock, degassing of oversaturated groundwater, or direct input into a trap as a free gas phase. And the trap information about the trap in regards with integrity and longevity. You can get microseepage, capillary failure, it can fail due to fractures. You can actually have tectonic destruction of the trap, and it's the same for helium. Just a bit of an expansion on secondary migration mechanisms. The free gas phase from primary migration can migrate directly into the trap, again facilitated by fracturing, buoyancy, and faulting. Free gas phase with the primary migration gases like the helium and the nitrogen and the CO2 can contact groundwater where it degasses due to contact with another gas phase. It'll remain dissolved in groundwater and moves laterally, picking up crustal gases as it moves until the groundwater is oversaturated, where you get a temperature change, salinity change, or a pressure decrease, where it contacts another gas phase, whereupon this groundwater will degas and go into the trap. You can also get stripping. This is where CO2 and or methane from a separate gas phase interacts with groundwater containing that helium and associated nitrogen and removes them from the groundwater when the two gas phases meet. All right, now we're getting to the good stuff. So here is the distribution of helium in Western Canada. And just a couple of words about this. This is not the entirety of the data. When I showed the lithium, that was all the data that was available. This is a subset of all the data. If you go into GeoScout and you can look at all the gas analysis data, there are just under 800,000 gas sample analyses that contain helium concentration data. To put them on this map, we wouldn't be able to see any of the things I'll be talking about. It would just be a blob of data. So what happened here was that we visually inspected the data to remove obvious contaminated samples and then filtered to show helium values greater than 0.3 mole percent. Similar to the lithium, the cooler values are the lower concentrations and the warmer values are the highest concentrations. And we find with helium that many of the highest values are hosted within Precambrian, Cambrian, Devonian, and Mississippian age strata. When we look at this data as it's posted here, there is a bit of a bias, as you will get spatially higher resolution data, aerially higher resolution data in areas with greater number of wellbores. And the reason that this 0.3 mole percent helium cutoff was used is simply that wells with this helium content or higher can be commercialized solely for their helium content. So let's look at the helium with respect to some of the basement properties and structural properties. So if we plot helium concentrations versus basement tectonic domains as a first approximation, there's not really a significant relationship between terrain age and helium concentration. All parts of the map with recorded helium values are underlain by Precambrian basement, and map areas showing elevated helium values, as I said in the red, are underlain by basements spanning multiple ages. from Archean rocks of the Huron province in the south to lower Proterozoic terranes, such as the Chinchaga and the Buffalo Head terranes in northwestern Alberta, as well as lower Proterozoic magmatic arcs, such as the Fort Simpson in northeastern British Columbia. Similarly, if we plot helium concentrations with respect to basement heat generation, microwatts per square meter, cubic meters, which is a proxy for radioactive decay, it's a fairly limited correspondence. Although, as discussed earlier, although higher rates of natural radioactivity produce helium, once generated, this helium has the potential to move laterally and would not necessarily accumulate in traps directly above these sources. One area where there's an exception to this may be southwest Saskatchewan, where you have helium concentrations in an area of somewhat higher basement heat generation, as well as northwestern Alberta in the Peace River Arch area here. And there are slightly elevated basement heat flow values in that part of the province. If we look at a correspondence between helium and tectonic and structural elements, this shows perhaps the closest correspondence between elevated values and these structural elements. Given the tendency of helium to accumulate within structural traps, this really isn't that surprising. Here we find that the helium accumulations in northwestern Alberta really seem to be coincident with both the location of the Peace River Arch as well as its structural atlas extending off to the northeast. And that is this area here. And there's the structural atlas of the arch. So we have a lot of high helium values here. This is the positive feature for a lot of the Paleozoic. You may have had migration of helium into that. Although these values may also result from the greater density of wells drilled in that area. But it is possible that local Peace River Arch associated faulting allowed vertical migration of helium into that structure. As well, you get higher concentrations of helium in southern Alberta. And this corresponds to the center and the northern flank of the Kevin Sunburst Dome. So again, another structural feature that maybe, at least in a gross sense, a regional sense, maybe trapping that helium. As well, in southern Saskatchewan, you have the dissolution edge of the prairie evaporite, and we're getting some elevated values there. And this may actually be associated with the edge of the swift current platform and the dissolution of that Devonian prairie evaporite. Again, higher helium values here may be an artifact of the greater number of wells drilled in that area, but may also be related to the vertical migration pathways provided by faulting associated with that structural edge. Helium regulatory framework by province. In Saskatchewan, it's 4.25%, and that's the royalty rate, and it has been applied to helium production since 1964. The province offers a 15% royalty credit for new helium processing and liquefaction projects. Since 2016, explorers have the ability to acquire a helium permit for to explore for helium reserves and then apply to convert their permit to a helium lease. Alberta announced a helium-specific royalty rate in May 2020, retroactive to April 1st that year. It's 5% minus a royalty adjustment factor of 0.75%, making it equivalent to that for Saskatchewan. In Alberta, helium falls under natural gas rights. British Columbia has not implemented a helium-specific royalty rate or announced other regulatory changes or incentives to date. So let's look at, operator activity in southern Saskatchewan. The past few years here have seen a dramatic increase in both land acquisitions and the number of licensed spudded and completed helium wells. And there are 5 operators currently developing helium in the southern part of the province: North American, Royal, the Whale Group, Canadian Helium, and Global Helium. So here is a land base for some of them. Keep your eye on North American Helium here. It's the one we're going to go into more detail about shortly. Here's Global Helium's land base, smaller areas and a little bit to the north of some of the others. So here is the operator activity in terms of the number of wells drilled for Canadian Helium, the Whale Group, Royal, and North American Helium. So let's focus in on North American Helium. So this is a private Calgary-based E&P company founded in 2013. It has that huge land base of over 1.7 million hectares in southwestern Saskatchewan, over 30 wells to date, drilled to date mainly in the Battle Creek and Cypress areas. It commenced first commercial helium production at its Cypress field in 2020 and opened a second larger production facility in May 2021. So combined, these two facilities currently produce 60 million cubic feet per year of purified helium. So let's zoom in here on one of the Cypress field wells. I just thought it would be interesting to look at one of these. So this is the 214-34-65-26 west of 3 well. It's targeting the Deadwood Formation basal sand unit. This is a vertical well, perf only completion. And the basal sand unit, you can see here, rests unconformably upon Precambrian basement. It's about 30 meters thick, and it lies at about a little over 2,400 meters depth. It exhibits excellent reservoir characteristics. It's a fairly clean sand. The neutron and density porosity are coming to meet each other. It's got great porosity here. And a gas analysis from the perf taken at the bottom here indicates 0.83% helium and 98.23% hydrogen, with 0.94% methane and C2 plus rounding out the analysis. So at 98.23% nitrogen, these are basically nitrogen wells that are being drilled, a little bit of nice helium in them. If we look at that core interval, we've actually got permeability up to just over 6 darcies, not millidarcies, but darcies at the high end, and porosity is going up to about 21 or 22%. So this is a great reservoir. So to summarize for helium, like lithium, its unique properties make it a really essential component of industrial and high-tech industries. The imminent shutdown or just past shutdown of the Federal Helium Reserve has motivated operators to seek alternate sources. New helium production is going to be mostly foreign. And there really is a need for a reliable domestic North American supply of helium. The Western Canada Basin has abundant helium resources and can help fill this need. We have multiple operators moving in to currently explore for helium in Alberta and Saskatchewan to develop this resource, and commercial extraction and purification of this has already begun in Saskatchewan. So Canada has an important role to play to meet future rising demand. Sorry about the bad pun. Okay, these are the ultimate conclusions. So both lithium and helium are critical minerals for us and our international partners. They're both abundant in the Western Canada Sedimentary Basin and can be extracted commercially. Canada is geopolitically stable and adjacent to the United States, which is a huge market for both of these elements. And there's this immense public subsurface database from past and current oil and gas exploration, which exists for the Western Canada Basin. as well as a highly skilled workforce and the technology know how to make it happen. So these can ultimately be potential new extractive industries working in parallel with our existing oil and gas industries. To finish off here, I'd like to thank CSIR for the opportunity to give this presentation, my colleagues at CDL for their technical assistance and feedback during preparation of this presentation. Contact details, here I am. You can also reach out to our sales staff, Adam Starolia and Krista Williams, or you can even reach out to our CEO, Kosh. And this will eventually be online at canadiandiscovery.com. Thanks very much.